So parametric equations. So this is actually, if you want to learn more about these, this is coming from section 10.6 in our textbook. So there are some parts here that actually come back to like conic sections. Like there are equations of hyperbolas and ellipses and stuff that we're going to be talking about in this lesson. So it is sort of related to what we're talking about this week. But basically, what is a parametric equation? So it's an equation where instead of just graphing x and y, you're graphing x and y over time. So I found this animated image. Basically, normally when we graph something, we just see the graph, and that's what it is. There's nothing moving parts. But since this is graphed over time, you actually can see how the graph is created as time goes on, and so it gives you a sense of like direction, and it kind of gives you a sense of speed for whatever equation you're looking at. So you are still graphing things basically in x and y, but now your input is time instead of x, and you've got two output equations, and those are used to create your ordered pairs. And so parametric equations, which I just realized that I spelled it wrong. Here, let me fix that. Parametric equations. They're actually used a lot in engineering and AC current, because current, when you're in alternating current, it does change over time. It's not static like it is in DC. And so there are a lot of equations in engineering dealing with that kind of stuff where you actually are looking at how the current changes over time. And so you are looking at parametric equations, or you'll be given equations and you'll have to make them parametric. So why do we use parametric equations? Well, there's lots of reasons. One of them is that sometimes when you're working with equations, they can be very, very complicated, and sometimes writing them parametrically actually makes them simpler. So it can take something that looks pretty complicated and actually can turn it into something a little simpler than it was before. So that's one reason why we have parametric equations. Another way is sometimes there are things that are really hard to write with a single equation, and so if we use parametric, we can kind of use two equations, an equation for x and an equation of y, to write that same thing. And that's what's usually used in calculus and engineering. I actually, when I was doing my research for my master's thesis, was we were doing calculus over various shapes, like squares and diamonds, and there is not, like, there's an equation for circles, but there's no single equation in x and y for squares and diamonds and things like that. So I had to create parametric equations so that I could create those shapes, because there isn't a single equation in x and y that does it. Parametric curves are actually really neat. So I have a couple links here. Wolfram Alpha is amazing. But let's see if I can get the link to work here. If I can get it to actually click. Maybe. There we go. Okay. So I have links here, so you'll have these in the PowerPoint. But you can use parametric equations to create really fun graphs. So this picture was not made in x and y. It's made entirely in a parametric equation. So it's a really nasty looking one, but you can use it to do really cool things. So you can, if you're interested, you can actually see what the equations are. There's an equation for x, which is this really complicated thing, and then here's the equation for y. But it's sort of like an Etch-a-Sketch, where everything is kind of connected, and so you could draw really neat things using parametric equations. And these are things that like people have come up with. People who are bored, they do these things. So there is just this other link has a whole bunch of them. So there's the Einstein one, there's Santa, Nelson Mandela. I know there's a Batman curve. Yeah, you've got the Batman one right here. There's one of Psy, who did the, that was several years ago, the Korean guy who did the Gangnam Style. So there's one of him. there's all these different curves made from parametric equations. So it's like this little thing that like you can really go crazy with. Like, let's just click on mean curves and see what pops up. So they've got all of these different kinds. So, and these are all parametric equations. So, I mean, it's crazy. You can get yourself really, if you just want to play around with this, you can go pretty deep with the parametric equations. But they're used for fun. That's another reason. You know, we have them. We can do some really neat things with them. The textbook, this is an example from the reading in 10.6, and I don't think that the textbook really did a good job of explaining it. So basically, if you're kicking a football, let's say you're kicking at an angle of 45 degrees at a specific speed of 48 feet per second, you can get this parabola. It doesn't tell you how they came up with that equation, but that's the equation. And so I plotted that. And normally when you plot that equation, you're plotting the horizontal distance and the vertical distance. So you can see I was able to put in the goalposts and stuff in there, but you don't know where it was at any time because you're not plotting time. You're just plotting horizontal and vertical distance. But if we take that equation and we convert it to parametric equations, then we can figure out where the ball was at any time t, because we've added a third variable t. So when you plot the parametric equation, it's going to look like this, but the numbers you plug in will be a series of points at time t, and when you connect them, they'll give you the basic shape here. So rectangular coordinates are what we normally use with x and y, and so parametric does give us some additional information, because rectangular, all you have is the whole path. You don't know the direction that it went, you don't know how fast it was going, you don't know where it was at any point of time. But with parametric equations, you get the path, but you also can figure out where it was at any point in time. It actually can give you the direction, because as you plot the points, you'll know which direction it's going. And you can figure out the speed, because if you know the distance it's gone over a certain amount of time, speed is distance over time. So you can actually use your equations to figure out speed of the object as well. So it gives you a lot more information than just our normal x, y. So here's where we're going to start getting into the more complicated, or mathy bits, is the definition of a plane curve. So if f and g are continuous functions of t on an interval I, then the set of ordered pairs f of t comma g of t is a plane curve C. So basically, you're taking two functions that are in t, where your input is time, and they give you two outputs. And those are considered your x and y values that create an ordered pair. And so those are the parametric equations, and then t is called the parameter. Now, basically what this means is that we create ordered pairs from parametric equations, we plot those, connect them, they form a curve, a plane curve. That's basically what it is. And you don't always have to have t for time. All the examples that I showed on Wolfram Alpha use t as the input, but they're actually in terms of angles. Because if you look at it, and let me pull that back up again, if I can. If you look at the equation is using trig functions, so they're actually in terms of, like, you're plugging in an angle. It's not just necessarily time, it's an angle. So you can plug in from like 0 to 2 pi. So you don't have to always plug in time, you can also plug in a rotation or an angle for your parametric equations. And those are the two common forms that you're either plugging in t or you're plugging in theta. So how do we graph these things, basically? And you have your equations that are in terms of t as your input, and you pick values of t, you plug those into both equations to get x and y values, and then those are your ordered pairs that you plot. And the key here when you're plotting these ordered pairs is you need to plot them in order from increasing values of time, because t is increasing, time increases, and that will give you the direction, because when you connect them, you then draw an arrow indicating where it's heading, and so that's how it gives you direction, and we call that the orientation. So you can see, you know, where does the thing go as we graph it. So I've got this first one sort of set up already. So we're going to sketch and describe the orientation of the curve given by the parametric equations. X equals negative t squared plus 3, and y equals t over 3. And then we're going from negative 2 to 3 as far as t. So I already created a table, and I'm just doing my values for t from negative 2 to 3. And then you fill in your table for x and y by plugging those into your equations. So the thing you want to be very careful about here is that you're actually plugging in the correct numbers into the correct equation, you know, because you've got two equations here. So you want to be very careful you're plugging in the correct stuff. So I'm actually going to bring up Desmos so that you can see how to kind of do this without messing it up. And you can even use Excel to make the table values if you want, if that's something that makes it easy. I think I did already open a tab for Desmos. So if you want to fill in a table like this, if you hit the plus, you get a table. And you can actually do like 3 at a time here. So we can also, let's see, so I can change, let's change this input to t, and then let's change this to x1, and then I think I should be able to also do a y1 here. So my t values are negative 2 to 3, so I'm going to just do whole numbers here. Oh, and it's even caught the pattern for me, awesome. Now, I think, I'm going to do this, I think what I can do is actually put in the equation for x1, or our x was negative t squared plus 3. Okay, I didn't like that. I've done this before, I'm just trying to remember how I did it. Okay, I know I can do this. I wonder if I put it here. Equations are not allowed. Okay, so if I just get rid of, there we go. So I don't put in my labels. I just put in my what it's equal to. And then that will fill in your table for you. So let me shrink this down so you can kind of see it here. Okay. So ignore the graph for now because it is not graphing the parametric equation. Like it is not actually graphing what it should be, what it's graphing here. So ignore the graph. What we're looking at is the table. So I entered in for my first column here what I had for x, negative t squared plus 3. And so it used the value for t and it filled in that table already. I'm just double checking that it matches what I did by hand. Then we've got our next one, t over 3. So it took those same t values and it plugged it into your table here. So this is what you're doing, is you're basically first creating a table of values. And so I just used Desmos to create those for me so that you're less likely to make mistakes. But ignore the graphs because the graph part is not actually the parametric equation. It's trying to graph both of these as two separate equations. So I'm going to copy these numbers into here. And this just using Desmos to get this, once you know how to do it, it saves you a lot of time in calculating and not having to just use your calculator. And then I'm going to round to, or put it in fraction form. So these are giving you ordered pairs that you're graphing. And then you want to describe the orientation. So we're going to graph this by hand, and then I'll kind of bring it up in Desmos so you can see how you would necessarily do this in Desmos. But we're going to graph it by hand. So my x values are going from, okay, so 2, 3, 4, 5, 6, 2, 1, 2, 3. So I'm just going to count by ones for my, oops, those are my y values. Help if I actually, let's count by 1/3 on my y values. And then on the x, we'll count by ones. So I'm just using the table to just try to figure out what numbers I'm going to pick. So now you're going to graph your x and y values. So -1, we're at -2/3. And then at 2, it's -1/3. And then I'm going to connect those and then draw an arrow to show I'm going from the first point to the second point. Then I'm at 3, 0. So I'm going to connect those. Then 2 and 1/3. So you draw an arrow, and you can see the direction that this curve heads as you graph it over time. You can see that it starts in one area and then it starts curving. Then we had -1 2/3. And then 2, 3, 4, -6 1. So this is what a parametric, how you graph a parametric equation. You're taking values for time, and instead of connecting your points from like the smallest x value to the largest x value, you're doing it for the smallest t value to the largest t value. And so then you can see how it curves, and you can see how it changes over time, and you draw in the arrows, and that's what shows the orientation. So when it says sketch and describe the orientation, that's what the graph does. Those arrows are describing the orientation. So you don't have to write like an additional sentence or anything like that. But that is what our graph looks like for these parametric equations. And the equations themselves are still functions, but our graph doesn't look like a function because it doesn't pass the vertical line test. But these are still considered functions because the equations are functions themselves. So it's sort of separate from the idea of a function when you're looking at the graph, because we're not really graphing the same thing that we normally graph. So I'm going to bring Desmos back here. So as I said, this, what Desmos did with our table doesn't match our thing at all because it's not trying to do parametric equations. In order to get Desmos to graph parametric equations, you need to put it as an ordered pair. So your x for the ordered pair is -t squared plus 3, comma, and then you put in the y for the ordered pair. And so that will give you the ordered pairs for your parametric equation. You can tell it to, connect it, so you can see that it has the same shape we did. But the unfortunate thing with Desmos is it doesn't give you direction. So you can verify that your graph is correct by graphing it in Desmos, but you don't get the orientation of the curve. It doesn't tell you where you're starting and where you're ending, or where you're ending. So that's why it's almost better to do these by hand so that you can actually see the directions that it's giving you. And you saw that with the Wolfram alpha curves, those sample, the fun ones, none of those had arrows either. They don't show direction. So direction is something that you get only when you're really doing it by hand, because then you can see where it's heading. But you can at least get the shape of the parametric curves yourself by putting it as an ordered pair. And then if you hold down here, you can turn on lines, and then you can make it connect the lines. And it will connect it in the correct way. It just doesn't give the orientation. Are there any questions so far? Okay. So here's one, and here's an example where instead of t as our input, these are actually angles. Grabbed this one from, this is number 6 in section 10.6. I thought this was a really nice one because it's basically taking your parametric equations and then comparing them to a different graph. And this will help you maybe see the connection between the two. So we've got, consider the parametric equations. X equals 4 cosine squared theta, and y equals 2 sine theta. So we're going to create a table of x and y values using specific values for theta. So instead of the input of t, it's now theta. And then we're going to have x and y. And so we've got negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2. And then you're going to be plugging these into, you know, you can do it in Desmos like I did the other one, but with instead of t, you can use theta. I'm going to just, I did this already by hand, did the calculation, so I'm going to just write those in just to save some time, but you're basically just plugging in your values, and these are in radian, so you have to make sure that your calculator is in radian mode. But these are the values you get out. And so if we plot this, see our x is basically going from 0 to 4. And then our y is going from negative 2 to 2. So we're going to start just plotting the points. We've got 0, negative 2, then 2, negative square root of 2, which is about negative 1.4. So I'm going to just kind of estimate it right here. Then 4, 0. Then we have 2 square root of 2, so I'm just estimating where it's at. And then 0, 2. So that's the plot of the parametric equations. And it kind of looks like a sideways parabola. And then it says sketch the graph of x equals negative y squared plus 4, and how do the graphs differ? So I'm going to do that second part in Desmos. I'm actually going to graph both of these in Desmos. So first, let's do our parametric that we have here. So, and instead, I don't know how to, I don't think I can type in theta. Oh, I can get theta. Okay. So we'll do 4 cosine squared theta. That is really cool. And then 2 sine theta. Now, too many variables. I think there's too many variables. There's only theta. Maybe it doesn't really like theta. Let's just use t. Okay. So it didn't like that. Let's go back to the cosine squared. I thought maybe that was the problem. Whoops. Cosine. Okay. So we need to tell it. It wants to know it defaults t from 0 to 2. So we've got a couple of things to do here. First, our graph settings. We want to make sure, okay, I'm in radian mode because we're graphing with sine and cosine here. And then I actually want this to go from negative pi over 2 to pi over 2. So I do have to put in my angle values basically here to graph it. So that's matches. It just doesn't have the direction, but it's graphing our plot here. And now we're comparing this to the graph of x equals negative y squared plus 4. So I'm actually going to make this dashed so we can keep this part. X equals negative y squared plus 4. Maybe I should make this one dashed. And then it's really hard to see. Let me make that one no longer dashed. But they are on top of each other. You can see very slightly between the dashes that there's green from the other one. These are the same thing. So they're graphing the same thing. The parametric equations we had in terms of trig give the same exact graph as our x equals, but it only gives us a section of the graph, a specific section that we're interested in. So it only gave us this section. And generally, it gives you direction. And the graph that you get doesn't give you any direction. It doesn't tell you, oh, are you graphing this way or are you graphing this way? So that's how the graphs differ. They actually are equivalent. They make the same shape. They're just giving different parts, different amount of information here. So let me do this in a different color. Negative y squared plus 4 is for, like, it graphs over negative infinity to infinity versus our graph. That's one of the differences. And doesn't give direction like ours does. So parametric equations, you can graph the same things that we do normally in x and y. The equations look very different, but they can give you you can get the same picture, but you actually get more information. That's the point here. So eliminating the parameter. So this is what you do when you take parametric equations and you want to put them back in their original equation with x and y. You do what's called eliminating the parameter. This shows up a lot in differential equations. Especially, I know for sure, those going in engineering that have to go on to like ET 310, and you have to do some integration. You have to eliminate the parameter in order to do the integration. And so this is a technique that will be used throughout your later courses. And so basically what you do is you solve one of the equations for t, and then plug it into the other equation. So generally we solve the one that has x for t, so we can plug it into the other one and have it solve for y. Sometimes that's the harder one, so you could do it the other way around. But that's what you're doing. You're solving one, plugging it to the second equation, and now you have an equation in x and y, so you've eliminated your parameter t. Now sometimes you do have to adjust the domain when you do this, because notice our domain here only graphed x from 0 to 4, and so the graph with x and y had a larger domain. So sometimes you do have to add restrictions to get the same thing. Like say, oh, we really only want this from 0 to 4 on our x to get the same picture. So you do sometimes have to adjust your domain so you get the same picture. But that's basically what it is that you're just solving one equation for t, plug it into the other, you've eliminated parameter. So eliminate the parameter and write the resulting rectangular equation. So rectangular equation just means it has x and y. This graph represents the curve, adjust the domain as needed. So here they're not giving us any rules, any like values on the domain, like saying that t is going between this and this. So if they don't give you any restrictions on t, you don't need to worry about adjusting your domain. It's only when they give you restrictions on t that you have to adjust the domain once you convert it back to x and y. So the easiest way to eliminate the parameter here is to take the equation with x and solve for t. And so that's pretty easy. We can just multiply both sides by 4 to get 4x equals t. And then once you've done that, you plug it into your next equation, and that will give us y equals 4x squared. Then you simplify, and we get 16x squared. And that is the rectangular equation. These are equivalent. If you went into Desmos and graphed the 1/4 t and t squared, it will give you the same picture as the 16x squared. You don't have to do any adjustments on our domain. So it's pretty simple to eliminate the parameter, not that hard at all. Now here's another one. This one's a little trickier. Same directions, we just have different equations here. We have x equals the square root of t plus 2 equals y equals t minus 1. So you can decide which one is the equation that you want to plug it into, basically, whether you want to solve for t and y or solve for t and x. Generally, if there's something with a square root, we'll use that one because we don't really like square roots in our equations. Just you know, they're harder to work with. So if we solve the one with the square root, we'd be squaring both sides, no more square roots. Now, we do have to think about the domain here because this inside the square root has to be greater than or equal to 0. So we do have to kind of think about, okay, this has a specific domain. This is telling us if we subtract 2 from both sides, I can only plug in values that are greater than or equal to -2 for t. So we have to think about that. So this is one problem where you may have to adjust the domain. So let's take our equation for x, the square root of t plus 2, and so we're going to solve this for t. So you're going to square both sides, and then we subtract 2 from both sides. And so this gives us x squared minus 2 equals t. So now that we've solved for t, we need to also kind of think about going back to the domain. So if t has to be greater than or equal to -2, this is telling us that x squared minus 2 needs to be greater than or equal to -2. So when you solve this inequality, we get x squared is greater than or equal to 0, which is always true. So we're not going to have any problems with our domain. We're not going to have anything because when we convert it to our new domain in x, there's no restrictions. So the original domain was t has to be greater than or equal to -2. Our new domain, when we adjust it, is all real numbers because we got something that's always true. So we are adjusting the domain here from specifically greater than or equal to -2 to anything can be plugged in. So that's how you do that, is you basically you solve for t and you plug it into your domain and see what your new domain is. So our new domain is going to be all real numbers, and then we still have to get our actual equation. So we have y equals t minus 1. So we're going to plug in what we solved for t, which is x squared minus 2, and then minus 1. So this gives us x squared minus 3. And so this is the rectangular equation that represents the curve that we had in parametric equations. And just to make the domain thing clear, our original domain is -2 to infinity, but we did adjust the domain to be -infinity to positive infinity once we kind of did that check. Are there any questions? Okay. same thing. Now we are going to have equations in dealing with trig functions. And in order to, if you have any parametric equations that involve trig functions, if you try to just solve for like theta, you're going to get some really gross stuff that's not really going to simplify, because you're going to get like a, let's say if we solved x, we'd get an arc cosine or an inverse cosine, and then you plug that into your sine, and then those don't, the sine and the inverse of cosine don't really cancel out. So whenever you have something that involves trig functions, in order to eliminate the variable, we actually use our Pythagorean theorems. Those Pythagorean identities that we talked about last week, we use those. So having those handy is excellent. So first, let's just, the domain, when you ever have anything with angles here, so I'm going to do the old domain, and that is always going to be 0 to 2 pi. So whenever anything with angles, our domain 0 to 2 pi. So we do have to consider the domain and adjust the domain once we do this conversion here. And whenever you have domain that involves trig functions, the best way to figure out the new domain is to based off of graphing it. So that's the first thing that I'm going to do, is I'm going to bring back Desmos here. And so I'm going to put in, let's get rid of this. We're going to go from 0 to 2 pi. And then we've got 2 cosine t and 3 sine t. And why is that not graphing? I don't know why that's not graphing, so I'm going to just type it in again. Maybe it's just something about how I typed it in. It was working before. Oh, it was just really, really small. Okay, and we want 0 to 2 pi. Okay, there we go. So see how this actually gives us a straight line here. It's interesting. We have our parametric equations involve trig functions. Oops, that's why that's t. There. Okay, this is what I was expecting. I'm like, why is it looking like a straight line? Okay, this is, so notice this is what it graphs, our parametric equation. It actually graphs an ellipse. So whenever you have trig functions, if you tried to do what we did on the last one to kind of convert the domain to the new domain, sometimes you get issues. So it's better to do the graph. So we're going to just note that our new domain after we eliminate the parameter is going to be -2 to 2. So the domain is always like your input, your x values. So I'm just going to write that down based off of our picture, that the new domain in terms of x will be, oops, -2 to 2. And so we had to graph that to figure that out. So we just adjusted our domain. So now to eliminate the parameter, whenever you have things with sine and cosine, use the Pythagorean identity sine squared theta plus cosine squared theta equals 1. That's the Pythagorean identity that you're going to use. So actually what I should do first is I want to solve my equations here for sine and cosine. So we have x over 2 equals cosine theta, and then y over 3 equals sine theta. And then we're going to use our sine squared theta plus cosine squared theta equals 1. So sine squared, we're going to plug in y over 3 squared, and then cosine is x over 2, so we're going to plug that in, squared equals 1. And so when you square, we get y squared over 9 plus x squared over 4 equals 1. And this is the form of an equation of an ellipse. So we've been with the conic sections, we learned how to do these in x and y. Now, normally the ellipse has x first and then y second, doesn't matter. What's important is that this is the form of an ellipse. Its parametric form uses just cosine and sine. So this is our rectangular form. And this is one case where we actually prefer the parametric because rectangular has these x squareds and y squareds, but the parametric is actually pretty simple. All you need are sine and cosine. And you're using your angle 0 to 2 pi because you're rotating across the ellipse basically to get back to where you were. So example here, we did have to adjust the domain. Now here's another one with secant and tangent. Again, if you have trig functions, you're going to want to use the trig identities in order to get these. So first, we're going to look at the domain. So we're going to, I just like to take the domain first so that I don't have to, think about that or remember that or be like, oh shoot, I forgot to do my domain. So we've got 2 times secant theta, and then this is just tangent of theta. Okay, so I'm going to zoom out. So you can see that we are actually getting 2 sides of an hyperbola. And over 0 and 2 pi, we get both sides of the hyperbola. So we're not going to really have to do anything with the domain because the domain will be all real numbers essentially, unless we skip this middle part. But we can just say all real numbers will be good to go. If, say, we had the domain restricted, like let's say instead of 0 to 2 pi, it was pi over 2 to 3 pi over 2, then we would have to change the domain of the hyperbola to make sure that we're only getting the left side here, because that's what we have in our picture. But we don't have any restrictions on the domain based off of what we're given here, so we're going to we don't have to really change anything. It's going to be all real numbers. So just like I did on the previous one, we're going to solve for secant and tangent. One's already solved for tangent, so we're just going to solve for secant. So x over 2 is equal to secant theta. Now we're going to use the Pythagorean identity 1 plus tangent squared theta equals secant squared theta. That's the only one that we have involving tangent and secant. So we've got 1 plus tangent is y, so tangent squared is y squared. And then secant squared is x over 2 squared. So we get 1 plus y squared equals x squared over 4. And if you subtract y squared from both sides, then you'll see that we have the equation for a hyperbola. We have x squared over 4 minus y squared, and that's our form that we have for hyperbolas. So if you tried to find the domain any other way with something like this, if they had given us restrictions on the domain, like I had demonstrated, where it's only like the left side, and then you try to, maybe do some substitution and convert that to x or y, you would have some issues. So this is, whenever you have your trig functions, just always graph them to figure out what your domain is. Any questions so far? Okay, so you may be wondering, okay, well, how do I go the other way? How do I take something in terms of x and y and then change it to something that's in t? So doing this is called parameterizing the curve. There are multiple ways to do this. There is not really a wrong way to do this. There are certain types of equations that tend to get parameterized a certain way because that's the easiest way, but you can really do it any way you want. You just pick what you want to let equal to t, and then you go from there. So here's an example where we're telling you what to pick t for. So we're going to find a set of parametric equations to represent the graph of y equals 2x minus 3 using t equals 2 minus x. So our parametric equations, we need to have x equals and y equals. So we've got y equals 2x minus 3 here. To convert it into something in terms of t, we need to find x first. This equation we can solve for x. So we can, let's say we can add x to both sides, and I can have x plus t equals 2, and then subtract t, so you get 2 minus t as x. That is one of our parametric equations. You basically take whatever you decided t to be, solve for x, and that gives you one of your parametric equations. Then you plug that into your other equation. So x is 2 minus t, and you solve. So we get y equals 4 minus 2t minus 3. And 4 minus 3 is 1, so you get 1 minus 2t. So to represent the graph of y equals 2x minus 3, we can use these two parametric equations, 2 minus t and 1 minus 2t. So it's sort of like the reverse of what we had to do when we were eliminating the parameter. Now I mentioned that there's many different ways that you can do this. So if we go back to that football example, you could just say, okay, I'm going to replace x with t, and then you're done. You have x equals t, and then you get your second equation where you just changed everything to t. And that's a perfectly valid way to parameterize that. If you go to the section in the textbook where this comes from, they have much more complicated looking ones. They have 24 square root of 2, and then negative 16t squared plus 24 square root of 2. I think that's square root of 2t. I think I forgot my t there. So that doesn't have a t in there. It's supposed to be a t. 24 square root of 2t, and then they have their second equation. And those are actually coming from physics equations for projectiles with horizontal and vertical distance. So the book decided to use some common equations in physics to write their parameterized equations. And that last one there should be familiar because if you took college algebra with me, we did talk about that equation, negative 16t squared plus v naught. We didn't have the sign involved because we had a 90-degree angle where sine was 1, but we used that equation. And so that's actually that equation that we used is one of the parameterized equations. It only gives you vertical distance in terms of time. It doesn't give you your horizontal. But that's an example of how you can parameterize, is take some known information like a physics equation. So here's an example. Hopefully, let's see, I'm looking at how much time I have left and if I have enough time to do this. Yeah, we should be okay. We should have time to do this. Okay. So the center field fence in a baseball stadium is 7 feet high and 408 feet from home plate. A baseball player hits a baseball at a point 3 feet above the ground. The ball leaves the angle, or the bat at an angle of theta degrees with a horizontal at a speed of 100 miles per hour. So part A is to write a set of parametric equations that model the path of the baseball. We're going to use these two right here, the ones that are coming from physics. So we're going to use these two equations to model the path. And in order to do this, we need to make sure all our units match. So they give us the speed of 100 miles per hour. We need to convert that to feet per second. So just because I know I don't have a lot of time here, I'm going to just write that out. So our initial velocity is 100 miles per hour. If you go through and do the unit conversions, that comes out to 146.67 feet per second. And our initial height, we're 3 feet. It's hit 3 feet off the ground. So our two equations, x of t, or you can just do x equals, is v naught times cosine theta t. So v naught is 146.67 cosine theta t. We currently have an unknown angle for right now. And then our second one is negative 16t squared plus v naught times the sine of theta t. So that's 146.67 sine theta t plus your initial height 3. So I'm just plugging in the information we have into these two equations given from physics, and those are the parameterized equations. So part B says to use a graphing utility to graph the baseball when the angle is 15 degrees, and then is it a home run? So it's a home run if it goes above the fence 7 feet high at a distance of 408 feet. So we can put that in as an ordered pair. Our horizontal is 408 feet, and that's the height of the fence. So just zoom way out here. There we go. So that's where the fence is, and now we're going to, it says to use 15 feet. So I'm going to type in, we have 146.67 cosine of 15 degrees times t, and then y is negative 16t squared plus 146.67, not 68. Not that it really matters. 7 sine of theta, which we're using is 15t, or 15 degrees, and then plus 3. Now, I'm in radian mode right now. If I click here, I'm in radians. So if I'm going to use degrees, I just need to click this button, degrees. And then here, our t, it's only going to 1. Clearly, 1 second is not enough. If you remember anything from college algebra, it takes about 4 seconds to get to its maximum height. So it should take double that to hit the ground. So I can put 8 seconds here. More than enough here for this angle. But you can see that this is the path of the ball. It will go here, and then it will hit the ground before it gets to the fence. So part B says, is it a home run? No, it's not a home run because with 15 degrees, it hit the ground before it went over the fence. So the next one is 23 degrees. So all I need to do is change my angles to be 23 degrees. And then you can see that if you hit it at an angle of 23 degrees, you do go over the fence. And so then you do get a home run at an angle of 23 degrees. So Desmos is really nice here to help you visualize that. So this was no, this is yes. And then it says find the minimum angle required for the hit to be a home run. So you can do this by trial and error, or you can actually create a system of equations because you know that x and y, if it's you want it to be 408 and 7, so you can create a system of equations where you solve one of them for t, plug it into the other equation, you have only theta, and then you can solve for theta. You'll have two unknowns, t and theta. And you can actually solve, and you will get, I got 2 answers. One of them is not the minimum, about 19.4 degrees. Now, we've got 4 minutes, so we're not going to go through that, but for part D, in order to kind of find the minimum angle, you just create 2 equations. using the height of the fence. Now, ideally, you'd want to be higher than the height of the fence, so you can say maybe 19.5 or something around, a little bit higher. But you just plug in your numbers for X and Y for that fence. And then you solve your system. And this is not a linear system. This is a non-linear system, so you cannot use a matrix to solve this. You'd have to solve this by hand. You do need to use a trig identity to solve it, but you can. We know everything. You've learned everything you need to know to solve this. So if you want some practice on solving those and using trig identities, you would go ahead and solve the system. You'll end up having to use the quadratic formula, and you should get 19.4. So I'm probably going to fill in that math before I upload this, just so you have that. So this is my last slide, and this is just common forms of parametric equations so that you're not guessing how to write it. For lines, you basically use like point slope form in a way to get your equation where your slope is t. Or you can think of your slope as the difference between the two x values or two y values, but that's how you would parameterize equations of a line. Circle with center h, k, and radius r, that's how you would write the parameterized equation. So you're just plugging in your center and your radius. An ellipse would be h and k with cosine and sine, and you have values a and b in front of there. And then hyperbolas use secant and tangent. So we saw these last two forms, we didn't have any, they were centered at 0, or 0, 0, so the h and k weren't there. But these are common forms of parametric equations, so that way when you go having to do parametric equations later on, you can reference this and say, okay, I need to write a parametric equation for a circle. Here's the form. Just plug in your numbers, and there you go. You don't have to think too much about it. These are the typical forms that we use. So are there any questions